In 2019, scientists at Fermilab in the United States managed to measure the energy of empty space. They found that it's almost zero. That sounds pretty boring, but it was actually something of a catastrophe because according to quantum field theory, empty space should be filled with an enormous amount of energy. So why doesn't the universe collapse from all that energy? This is the so-called vacuum catastrophe. And while it might sound like science fiction, it's one of the most serious problems in fundamental physics today. Let's have a look. Quantum field theory says that all particles are excitations of underlying fields that pervade all of space. For example, the electron field, which is usually denoted with a psi, where this little cross thingy means that it's a field that has 3 dimensions in space. The electron field can be in different states. The state with no particle is the vacuum. We usually denote this with a bar on top of the psi. The energy of this vacuum state is usually also called the vacuum energy. And here comes the first problem. In quantum mechanics, the energy of a field isn't just one value but has a distribution of possible values. It has an associated probability distribution. And in the case of the vacuum, we'd like to know the probability to find an electron with energy. This distribution is called the spectral function, usually denoted with a capital letter, and it tells us that the energy of the vacuum can take any positive value with some probability. But the higher the energy, the smaller the probability. This already looks kind of weird, right? Well, yes, but this is just for one field. And the issue is now that we have a lot more than just one type of particle. We have all those elementary particles in the standard model of particle physics. And since every particle has its own field, we have a sum over all these contributions to the total vacuum energy. And this is where things get really weird. The spectral function of the vacuum for each of these fields separately looks like this. But if we add them up, the result is that the total vacuum energy gets a contribution from arbitrarily high energies. You see, the individual contributions from the different fields have these divergences at high energies. But when we add them all together, they add up to a finite value, and this value is not zero. It's this number, 10 to the 168th power times 1 over the Planck constant. Yes, that's a huge number. What does that mean? It means that empty space is unstable because it has a huge amount of energy and it could release that energy and collapse. That this hasn't happened yet is either because there is something wrong with our theory or because the universe is very young, but both aren't very satisfying answers. So what's wrong? Why do we have this vacuum catastrophe? I think there are 2 reasons. One is that people often misunderstand what these calculations mean and then draw the wrong conclusions. The other reason is that many physicists are just bad at doing maths. Let me first address the issue with the interpretation. These calculations are done with a mathematical framework that is called the path integral formulation of quantum field theory. In this approach, we calculate probabilities by summing over all possible histories, the paths that the system can take. The paths can go into the complex plane and describe all kinds of nonsense. Most physicists use this approach without having the faintest idea what it means, but you don't need to worry about that. What you need to know is that the path integral gives you a number that can be interpreted as a probability. Now, what's problematic is that this probability isn't normalized. What do I mean by that? It's that the sum of all probabilities isn't 1, but infinity. Or, to put it differently, the vacuum probability, that's the sum of all probabilities for all possible energies, is 0. This means that according to this calculation, the vacuum shouldn't exist because it would have a 0 probability. But just because the vacuum has a 0 probability doesn't mean it doesn't exist. It's a bit like if you're playing Monopoly and roll a 7, then you move into Go and collect $200. The probability of rolling a 7 is 0, but that doesn't mean you don't collect the money. Why is this so confusing? It is because most physicists don't understand that the probability interpretation of the path integral only works if you restrict yourself to a finite time interval. It doesn't make sense to talk about probabilities for infinitely long time. If you want to calculate the probability for a particular outcome for all time, then you've got to use the Born rule. It's named after Max Born, who unfortunately also didn't win a Nobel Prize. This is a completely different mathematical framework than the path integral, but it's equivalent. Okay, but then how did physicists come up with this weird energy spectrum of the vacuum? Well, this is because they used a mathematically correct but physically meaningless thing. It's called analytically continuing the path integral into the complex plane. I promise that you don't need to know what that means. The relevant thing to know is that it doesn't work for calculating probabilities. You can't use this result to say anything about what happens in reality. It's basically mathematics with some physical interpretation. So, what's all this good for? Well, I'll tell you in a moment. But first, let me address the second reason why we have this vacuum catastrophe, namely that many physicists are really bad at doing maths. Let me explain this. When you calculate this vacuum energy, you have to do an integral over all possible frequencies, or equivalently all possible energies. And the mathematician in me wants to tell you now that the integral over all frequencies doesn't exist. This means that the whole thing is nonsense. And that's indeed what the mathematicians have been saying for decades, but physicists kept on ignoring them. But hold on, you may say, I thought this integral exists because otherwise the whole theory would break down. Well, no, it's not an issue if the integral doesn't exist. It's just that physicists don't know how to do it properly. So they try to avoid it by introducing a cutoff at some frequency or some ultraviolet cutoff. If you remove the cutoff, the result will always diverge. But if you introduce the cutoff, then you get something that looks like this. You see, physicists keep on arguing about what this exponent should be. Is it 3 over 4 or 5 over 2 or maybe even 7 over 3? But this isn't the real problem. The real problem is that all these exponents are unphysical because the whole thing is mathematically meaningless. What would we need? We'd need to regulate this integral correctly. And the way to do that is something that's called the renormalization group. That's an entire research area in condensed matter physics. And believe it or not, it's not difficult at all. It's just that physicists don't know how to do it. They haven't solved the renormalization group for quantum field theory. And that brings me to what this all is good for. This mathematically correct but physically meaningless expression for the vacuum energy has inspired physicists to develop all kinds of approximations to calculate what it should be. For example, this holographic principle that you sometimes hear about, that's one such attempt. Another one is string theory, which, just so you know, is not a theory in the mathematical sense because it has not been proven. String theorists assume that the real world is 10-dimensional instead of 4. Then they assume that 6 of these dimensions are not infinitely large, but small, so small that we can't measure them. Then they calculate the vacuum energy for this 5-dimensional world and compare that to our 4-dimensional world. That they get something that looks like this. And that's supposed to explain why gravity is so much weaker than the other forces. This is the so-called hierarchy problem, but again, the whole thing isn't mathematically correct. This is just another example of physicists pretending that the vacuum catastrophe doesn't exist. There are many more examples. For example, the cosmological constant problem, that's the issue that we observe that the vacuum energy of empty space is close to 0, though it shouldn't be huge. Or the mass of the Higgs boson, that's the particle that's responsible for giving masses to other particles. Its mass is predicted to be much, much larger than what we observe. Both issues are related to the fact that we don't understand what the vacuum energy is. Summarized, the vacuum catastrophe is the issue that the vacuum energy should be huge but isn't. Mathematically, this means that something doesn't make sense. Physicists pretend that it makes sense and use meaningless expressions to motivate approximations that pretend that the problem goes away. What we really need is to solve the renormalization group for quantum field theory. It's basically a mathematical problem. Unfortunately, no physicist has solved it so far, though I'm sure that won't last long. Then again, maybe physicists are better at doing maths than mathematicians. After all, they've managed to solve the Navier-Stokes equation. Everybody knows that this is impossible. Many thanks to our sponsors, especially those of you in Tier 4 and higher. This channel would not be possible without your help. And you too can help us. Go check out our support page. Last but not least, thanks for watching. See you tomorrow.